Hello, we are KGHS 110 students. Today we are going to talk about Hooke's law. I'm Zoe. First, I'm sure most of us have heard the name Hooke's law during our studies. But have you ever wondered how Hooke discovered the unique properties of springs and how this seemingly simple formula plays an important role in our daily lives? Let's turn back time to the 17th century and explore how this scientist helped change the world of physics. In the 17th century, Dutch physicist Christian Huygens invented a more accurate timekeeping device, the pendulum clock. It worked by measuring time through the steady swinging of a pendulum. However, Hooke realized that the pendulum motion was easily affected by external shaking, making it unstable and less precise for measurement. This led him to wonder, is there a type of motion that can maintain a fixed cycle in a stable manner even with outside disturbances? Eventually, he found an answer in something that also vibrates regularly but is much less affected by external forces, a spring. Through a series of experiments, he discovered that within the elastic range, the elongation of a spring is directly proportional to the force applied to it, such as the number of weights helping from it. This became what we now know as Hooke's law, F equals K times X, where force equals the spring constant times the deformation. This discovery wasn't just a theoretical breakthrough, it also made spring a much more accurate measurement tool. For example, in mechanical watches, Huygens later used a type of spring called a balance spring together with a metal ring. This combination created a mechanism that could keep time more precisely and wasn't affected by motion or shaking. Beyond that, the principle of Hooke's law is found in electronic scales, shock absorbing systems in buildings, and many more everyday technologies. Hooke's research not only helped us understand the nature of elastic forces, it also gave us a more reliable ways to measure, innovate, and apply science in our daily lives.
I'm Emily. Today I explain this exam question for you. Let's first look at the problem. A 5 kg wooden block is resting on a horizontal table. A spring with spring constant K equals 10 Newton per centimeter pulls the block straight upward. When the spring is stretched 3 cm, which statement is correct? Use G equals 10 meter per second squared. A. The block's weight becomes 20 Newton. B. The blocks move upwards with acceleration 6 meter per second squared. C. Before the spring pulls, the table gives a normal force of 50 Newton. D. After the spring pulls, the blocks leave the table and the normal force becomes 0. E. When the spring is stretched 6 cm, the block's acceleration is 2 meter per second squared. To solve this, we will use 3 laws and concepts. 1. Hooke's laws. F equals K times X. K is 10 Newton per cm. X is stretched in cm. 2. Weight equals M times G. 3. Newton's second law. F equals M times A. Now, step by step, the spring force is F equals 10 times 3 equals 30 Newton upwards. 2. The weight equals 5 times 10 equals 50 Newton downwards. 3. Net force equals 30 minus 50 equals negative 20 Newton. And acceleration is negative 20 over 5 equals negative 4 meter per second squared downward. This diagram shows the situation where the block is being pulled upward but hasn't left the table yet. First, the red arrow represents gravity, 50 Newton downward. The green arrow represents the spring force, 30 Newton upward. The purple arrow represents the normal force, 20 Newton upward. The normal force is the force from the table. Since the spring already provides 30 Newton upward, the table only needs to give 20 Newton to balance the total downward force. Here we can see that the forces are balanced, so the blocks do not move. So the block is still on the table. It does not lift up yet. Now let's check out each option. A. Wrong. The weight is always 50 Newton. It does not change. B. Wrong. Acceleration is minus 4 meter per second squared downward. However, due to the positive force given by the table, this acceleration will be blocked. C. Yes. Before the pulling, the table supports all the weight, 50 Newton normal force. D. Wrong. The block doesn't leave the table. Spring force is not enough to lift it. E. Try scratching to 6 cm. F equals 6 times 10 equals 60 Newton. Net force equals 60 minus 50 equals 10 Newton. And A is 10 over 5 equals 20 meter per second squared. The answer is correct. So the final answer are C and E.
I'm Clarissa. Today I'm going to walk you through a physics problem from GSAT. This question is from the 2018 Taiwanese College entrance exam. The problem states that the two springs connected to both ends of the mass will deform depending on the acceleration experienced by the object. In this case, the device is used to measure the gravitational acceleration. Here's the question that we're going to talk about, and we're going to infer the value of gravitational acceleration from the deformation of the springs. Before solving the problem, we need to use Hooke's law, which is expressed as F equals kx. The spring force equals the spring constant times the extension of the spring. According to the description, we can draw a schematic diagram. After the mass is subject to downward gravitational force mg, the upper spring is stretched by the downward pull and produces an upward elastic restoring forces Fs1, while its length becomes d1. The lower spring is compressed by the downward force and generates an upward restoring force Fs2, with its length changing to d2. The force Fs1 equals the spring constant k multiplied by the extension d1 minus d0. The force Fs2 equals the spring constant k multiplied by the compression d0 minus d2, ensuring the value remains positive. Since the object is at rest, the total upward force must equal the downward gravitational force mg. From this, we can set up the equation shown in the diagram. Factoring our k gives the second equation, and after rearranging terms, we can get the gravitational acceleration. The gravitational acceleration g is equals to the spring constant k multiplied by the difference between d1 and d2 divided by the mass n. Finally, comparing with the answer choices, we can see that the correct answer is D. This concludes our explanation. We hope our discussion has provided you with a deeper insight into this question.